So let's go ahead and let me see if I can pull up PowerPoint slides for Chapter 5 here. Okay. Chapter 5. That up. And actually, let's see here. I'm going to try and share a file here. By Q questions, do you mean like the Q is equal to M times CS delta T, those types of questions? Okay. Oh, files in use. Okay, let's stop using the file then so it can be shared. Things are getting a little bit spicy in the chat. Okay, well, where is it? Failed? Uh-oh. Let's try that again. I am trying to share a file for you all to look at here. And the first attempt to share it failed. If it doesn't work the second time, I'll just go to the whiteboard and I'll make up some stuff. It's thinking, it's thinking. Oh, I think it's going to work. Okay, you said Q. Will the practice exams still be useful? They will have more limited usefulness, that is for sure. Alright, can you see the PowerPoint slides on the screen? Yes, okay. Awesome. So, just to remind you of what this equation that you were asking about, what this is covering here. Well, is this going to work? Yikes, what is going on? I don't know what that was, but I don't like it. Let's try that again. Why is that not working? Okay, there we go. So, sorry, just trying to work out how to draw on the screen here, and it was freaking out on me there for a second. So this equation is talking about how when you either add in heat to an object or pull heat out of it, just depending on what you're doing, that is the Q portion here is the heat. So as the heat changes, how the change in temperature, or how the object will change in temperature as a result of that. So Q, the heat, is equal to the mass of the object times the specific heat of that object times the change in its temperature. And so we did a few example problems with this. And actually, let me find a different example, one that's not, we haven't already worked out. Let's find, okay. Let's see here. Actually, why don't I just make one up? I can just make one up. These are fairly easy to make up. What does that do? Go back to just being a whiteboard, perhaps. Let's stop sharing that. And let's do it this way. Okay, so let's say that I have found a piece of silver. And I want to raise the temperature of my nugget of silver from, I don't know, let's see, maybe we found it in some ice water. So it was at 0 degrees C, and we want to raise it up to a nice warm temperature of 28 degrees C. And the size of my nugget of silver is, let's see, we'll say we got a big piece of silver. It's going to weigh 107.1 grams. So we have 107.1 grams of silver. We're raising it from 0 degrees C up to 28 degrees C. And the question that I have is, how much energy is it going to take to do that? How much heat is it going to take to do that? So given what I've told you already, what are we going to need in order to solve this problem? Does anyone know? There's something that we're going to have to go and look up somewhere else. What is that? The specific heat. Yes. We need the specific heat capacity, or the heat capacity, or the specific heat, or whatever you want to call it. So we are going to then look in the book to find that. And I am looking through here right now to try and find that myself. Where is that? I know it's here. There it is. Okay. So when we look up the heat capacity, what we find is CS for silver is 0.235 joules per gram degrees C. So we also need to be able to remember the equation that we're going to use for this, which is this one right there. Q is equal to the mass times the specific heat times the change in the temperature. And we should be able to recognize that this is the equation we want to use, because this is the only equation we have that has to deal with heat and the change in temperature. There's literally no other one. So this is the equation we want to use. We're trying to find Q, and so because we are given the mass, we found the specific heat from the book, and we're told how the temperature is changing. We have everything we need to work this out. So we can go ahead and plug everything in. So Q is equal to 107.1 grams times the specific heat, joules per gram degrees C. And then if you remember, delta T is always final minus initial. So the final temperature, the temperature we're going to, is 28 degrees. The initial temperature is 0 degrees C, which is going to give us just 28 as our value. So if we do that math, let's see here, 107.1 times 0.235 times 28, we are going to end up with Q is 705 joules. And we know it's joules because the grams cancel and degrees C cancel. And it does cancel both of those out because when you do the subtraction, you're left with just 1 unit of degrees C. So 705 joules is our answer there. If you think about that answer, it should make sense, because the silver is our system, and we are warming our system up. It's going to a higher temperature, and so it should make sense that Q ends up being positive, because our system is gaining heat. So it's difficult to say for sure if the exact number makes sense, but it at least makes sense that the sign of Q is positive. Okay, let's do another one of these. And I am still recording this, so if you if that was too fast for you, you can always go back in and watch this later. So let's do another one of those that's kind of similar but a bit more complicated. Let's say we took that piece of silver. So we just had that piece of silver, and now I've forgotten what the mass was. I want to say it was 107.1, I think. Yeah, 107.1 grams of silver, and we had it at 28 degrees C. Let's say we take that piece of silver and we drop it into, well, why did I write that? Into. I don't know why that happened. We drop that into a cup of boiling water. Let me make sure I know where I'm going with this. This is always the risk when I make up a question in my head, is I end up making it too complicated. Oh, I think that's going to be too complicated. Okay, yeah, let's do it this way. Okay, so let's say originally I was going to have us find the final temperature, and then I realized that that was going to be like that crazy long problem we did before, and I don't want to do one of those. So instead, what we're going to do is we drop that same piece of silver, we raised it up to 28 degrees C. We dropped that into a cup of water that is at the boiling point of water, which is 100 degrees C. And when we do that, when they reach thermal equilibrium, let's say they both end at 30.1 degrees C. So this is the final temperature. For both the water and, or actually no, let's not say 30. Sorry, that's a bad number. Bad number. No. It's going to give us really, really weird stuff. Instead, they both end at 98.1 degrees C. Sorry about that. So 98.1 degrees C is the final temperature for both the water and the silver. All right. So, given this, And I think we have enough information here to work this out. Given all this information, what is the mass of the water? How much water was in our cup? So this is going to be a two-step process. What we're going to do is we have to figure out, given the temperature change that happens, how much heat must the metal have gained? And once we work that out, we can use that to work out how much energy, how much heat the water must have lost. And knowing that, we should be able to solve for the mass of the water. So let's go ahead and do the metal part first. So Q for the metal is what we're going to look for here. We already know that we have 107.1 grams. The specific heat for that was 0.235 joules per gram degree C, if my memory serves me correctly. And delta T is going to be 100 minus 28 degrees C, which is 72, I guess. Degrees C is that. Sorry, that looks like I'm saying the whole thing is 72. It's just this one part is 72. So if we do that math there, 107.1 times 0.235 times 72, the metal gained 1,812 joules of energy when it was put into that cup of hot water. So if it gained that much energy, what that means is that Q for the water, assuming that nothing else was gaining or losing energy, Q for the water had to be, I shouldn't say the opposite, but that same value but negative. If the metal gained that much heat, the water lost that much heat. So hopefully that makes sense. Again, we're making the assumption that the only thing transferring heat is the metal and the water. But if we make that assumption, then whatever heat the metal gained, the water must have lost. And so if we set up a new equation now with data for the water, we just figured out what Q for the water is. The mass of the water is what we're trying to find. We already know delta T for the water because we're given the initial and the final temperature, so we can work that out. And we can look up C sub S. We can look up the specific heat. So we have everything we need. So if Q is 1812 joules, M is what we're trying to find. CS, if you go and look that up, is 4.184 joules per gram degree C for water. And delta T is going to be, let's see, 1.9 and a negative 1.9. Because that is 98.1 minus 100. Yes, Fabian, what's your question? Oh, yep, actually you're right. That was a mistake on my part. So that should have been 98.1. So that's going to change our number a little bit here. It's not going to make a dramatic difference, but you are absolutely correct. That is not right. So let's see. 98.1 minus 28. So instead of 1812, it's 1764. But it is still negative 1764. So sorry about that. Thank you for that catch, Fabian. So we have negative, that's what I get for trying to do this stuff in my head, I guess. So we have a negative 1.9 is our delta T for the water. So at this point, we have everything that we need to solve for the mass. So if we take that negative 1764, divide by 4.184, and divide by negative 1.9, we get the mass of our water is 220, well, with sig figs, it'd be 2, well, I'm going to give myself 3. Even though I only have 2 there, I'm going to say I have 3 sig figs. That'd be 222 grams. Which is, it's about the size of a coffee cup full of boiling water. All right. Was that helpful? To those of you to the left, I noticed we lost a few along the way there. Hopefully that's a good kind of to get you back thinking in terms of what we're doing here. Actually, let's do one more of these before I call it for this session, because I'm kind of starting to lose my voice as well, and I have 2 more of these to do tomorrow. I probably should not have just been recording videos all day yesterday and all day this morning. If I'm going to be on chat session all afternoon as well. So let's go ahead and do one more. I want to do one that is over the last thing that we talked about before we went off for the never-ending break, and that was the standard enthalpies of formation. So if you remember, let me wait, that's not what I want. Let me share that file again with you all. So the last thing, goodness, why is that doing that? Okay. Ooh, that looks funky. Why is it doing that? Why is it doing that? Let me stop that and try that again. It's like it was overlaying the PowerPoint on top of the blackboard or the whiteboard that was there. It's not supposed to do that. And it's still doing it. Okay, that's, I guess we'll just have to deal with it. Even though it was really not supposed to do that. So we were using the standard heats of formation to find enthalpy values for reactions. So if you remember, the way that we did that was just using tables of standard enthalpies of formation. So we took a reaction that was taking place, and we said, given this reaction, what is the enthalpy change that occurs? And the way we would find that was just by taking the products and their standard enthalpies of formation and subtracting the reactants. Products minus reactants. That's how we found the enthalpies of those reactions using the values from the table. And again, that just looks, see, I don't think that's actually, I think it's just something, the way that it's sharing that is just not right. It's like it has white text and then black text that are just slightly offset. Oh, somebody's writing on the screen. I'm going to have to find a way to keep everyone from writing stuff all over this. Oh, you're fine. You're fine, Fabian. As long as you don't start writing obscenities on the screen, it's fine. So let's go ahead and do one of these real quick. We'll do the last one here because I don't think we actually did this one in class together. So this asks us to find the standard enthalpies of formation to determine delta H for the reaction. And this is something that I would expect you to be able to do on the exam. So I would do something similar to this. I would just say, here's a reaction, find the enthalpy change for this reaction. And I would expect you to have your book available. And by the way, even if you don't have a hard copy book, you can download the PDF, and the appendices are right at the back as well. So you can get your appendix out, not your biological appendix, but your book appendix, and find the enthalpy values for those things. So let's see here. Delta H is product minus reactants. So for this particular reaction, delta H is going to be 4 times the number for no. And the way that these appendices are usually arranged is alphabetically by element, and so they kind of pick a main element, so to speak. And so for NO, the main element is going to be nitrogen. And if I go to my appendix and find nitrogen monoxide in the gas phase, I see it has a value of 91.3 kilojoules per mole. And by the way, all these are going to be kilojoules per mole. I'm going to leave that out just because I know I'm going to run out of space. So I'm going to have 4 times 91.3. So that's the no. That's my first product. I'm going to add to that 6 times the number for water, because we have 6 waters. So water would be listed under oxygen. Alright. I'm going to do my best not to recite the ABCs as I'm trying to find things alphabetically. So 6 times water in the gas phase is negative 241.8. Okay, so those are my products. So products minus reactants. I have 2 reactants here. I'm going to have 4 times the number for ammonia. Going back to nitrogen here. So ammonia, in my appendix, it says that gaseous ammonia is negative 45.9. And then I'm going to have 5 times the number for oxygen, which if you go and look, you will see that because it is a free element, that is the elemental form of oxygen, it is going to be 0. So I had a little bit of work there to look stuff up in the appendix, but it wasn't too bad. So I found the numbers for each of those things. I multiplied them by their coefficients, and then I'm just going to do products minus reactants. So again, this is NH3, and that's O2. And so if I do all of that math here, 4 times 91.3 plus 6 times 2, negative. It's very important to remember those negatives, so negative 241.8 minus 4 times negative 45.9 delta H for this reaction is negative 902 kilojoules. And those per mole values go away because we're actually multiplying by the number of moles here. So this is 4 moles, and this is 6 moles, and so the per mole value actually goes away. We're just left with that is how many kilojoules are released in this case, because it is a negative value, so that is an exothermic reaction. That number of moles are released when the reaction occurs as written. So this is definitely something that I would expect you to be able to do on the exam, where I just give you a reaction and just say, find delta H for the reaction. And all you would have to do is just exactly what we did here. Products, their numbers from the appendices multiplied by their coefficients, minus the reactants, where it's just the same thing. The number from the appendix times the coefficients, and so products minus reactants gives you delta H for the reaction. All right. Any last minute questions before I let you go for today? Okay. I guess I will let you all